being able to go back and forth between the whiteboard and the slides. We're going to do things a bit differently today. Hopefully it's not too weird. Let's see. Okay, it's 10:45, so I said let's get started. Are there any questions about the project or the content of the previous or any other lecture before we get into the further content? I uploaded the notes for the Tuesday's lecture last night, so I recommend that you check it out. The whole lecture was really hard to teach. It's a really convoluted material even for myself. So I tried my best to kind of break it down into notes, and I think it's the best kind of exposition of that content I can give you. And I think it's worth reading through the notes even if you were at the lecture last time. Okay, I don't hear any questions, so let me just remind you what we were talking about last time. In general, now we are focusing on attention heads. Remember I said, and you all know that attention mechanism is really important in the transformer architecture. And of course, then researchers were examining attention, and one line of work tried to understand what these attention heads are doing mechanistically. So try to identify some heads and say what kind of process, what kind of algorithm they are implementing. And that line of work all stems from that mathematical framework work which we use to define residual stream. And in that work they use very toy models, and they progressively make them slightly more complicated. And in these toy models they are looking at what kind of things these attention heads are doing. So last time we derived a zero-layer transformer, which is very funny to even say because it's just a model that takes embedding. It takes a token, embeds it, unembeds it to get the probability distribution over the lookup. So basically, this is the here WEWU. That was our zero-layer transformer, right? And then we said, well, all this model does is what I exactly said right now. It takes a token embedding, it unembeds it, meaning it produces a probability distribution over the tokens in the lookup. And I should stop saying probability distribution because we work with logics. This just comes from the habit that we usually use softmax in this interpretability stuff. We usually use logics to avoid that nonlinearity at the end. So more precise way of saying what I just said would be likelihoods of next tokens given current token. And when you think about, okay, if I have this token and then I have all the possible continuation of that token, I'm basically producing a bigram, a sequence of 2 consecutive tokens, and I have also likelihood of that bigram. So we said, all right, zero-layer transformer, all it can do for us is given current token, it can give us the likelihood of the next token, and that simple model is basically calculating bigram statistics. Then we move into one layer attention-only transformer, meaning we are only keeping residual connection in one attention layer, but one attention layer can have multiple heads, and we are using that notation from the mathematical framework where we are saying that attention heads are additive and independent. So x1 is the output of, it's a residual connection. So this plus denotes residual connection. It's what is input to the multi-head attention, right? So x0, which is just embedding tokens, are input to the input to the multi-head attention. This is just that additive independent write-up of the multi-head attention. And here we have our attention matrix, and we did a little bit of refactoring by defining the weight matrices QK and OV, and then just refactored how we usually write this into term like this. And this gives us these 2 additional matrices, both that are square in the size of the lookup. And we call these 2 matrices query key circuit and OV circuit. So that was one of the really important things we have done last time. One of these terms you will keep seeing in the mechanistic interpretability literature. And then kind of the way to read these 2 matrices I said was, well, query key tells you for every single possible token, given its token with that token, if it was a query, how much it would attend to all the other tokens in the workup, which are our keys, right? And OV tells us, well, if we had attended to a certain token, how much of that token we would actually write in the residual stream of the token at the current destination position, right? So when we look into these OV matrices, I should say OV matrices that are folded together with these embedded matrices, we get the matrix that is square in the size of the lookup, and the way we can read the entry in that matrix is to say, okay, if I have ij entry, if I'm at that means that if the j token attends a lot on the I token, what would be the token that would be promoted? Sorry, if I have ij entry, that would mean if the token where I computed this thing is no, not really. Okay, let me not try to explain it in terms of the single entry. If you would read this matrix, it basically tells you if I attend to a certain token, how much other token logics would be promoted. And if you see that this matrix looks like a diagonal, it basically, or it's a heavy on diagonal, it means that if I attend to a certain token, that same token will be promoted as the prediction token, as the next token, right? And this suggests that this attention head is implementing something like copy, right? If I attend to a token, copy that token, predict it as the next token. And this is kind of where we stop. And if you remember, the last lecture also talked a lot about in-context learning, which is a way of prompting LLMs where we give some tasks, such as, let's say, translate this sentence from English to Spanish, but we also will give a few examples of how to do that task. So we give a few English sentences, but also few their associated proper Spanish translations. And then we give a new English sentence and request Spanish translation. And so now we come to how all of this can play a role for in-context learning. So next thing we could do is derive two-layer attention-only transform. Meaning now the input to the second layer at multi-head attention is x1, which we just computed, right? And we also have a residual connection, so we add x1 with the output of the multi-head attention and x1 is the input. That's our final representation. And now I didn't write it here, unfortunately, but then we would have, remember we were calculating what the logits are. So we would have t equals to x2wu, right? So I would take wu, which is my unembedding matrix, and multiply it with all of this. Now, probably you can see why I don't want to write all of that on the whiteboard. It would mean that now we need to just expand and expand and expand, and eventually we will get something that's so wide which would probably barely fit on the whiteboard. What we would see if I have done all of that is that whatever is the output of the first layer's head, it can be used by the second layer's head to determine what to record in the residual stream and make the decision. And because that can happen, we get the possibility that the first head can store, and maybe I will go to the next slide, it's going to be nicer. So a first layer head, ignore everything that's written, I'm going to talk about these two things. So a first layer's head can copy information from the previous token into each token's residual stream. So if I have, guys who are sitting there, do you see what I write here? Okay. So if I have tokens A and B, my first layer's attention head, when it comes to B and it's producing representations for B, can record in that vector representation information about previous token. So previous token's information can be recorded in the next token's representation. Now we have that representation. What the next head in the next layer can do, it can attend to the token, like the token B, and it can attend to it not because of the content of B, but rather because of information that A preceded B. So this is going to require a little bit of mental gymnastics, so pay attention. So head 1 does this. It takes information about A and it records it into information in the representation of B. And now head 2 has an input something like this. We have AB, and then we come to the token A again. Now this head can attend to B, but unlike one layer attention-only transformer that attended to B because of the content of the B, it really wanted to just copy B, this attention head can attend to B because it has information that A preceded B, and if A preceded B, and I'm currently at A, then what the next token should be? B. I mean, it's a little bit obvious if you don't understand anything that I just said, right? But I hope you follow me along, so I'll repeat it. With the one, our first layer's attention head can record information about A into B, and then the second layer's attention, when it attends from A to B, it doesn't attend to B because of what the B is. It can be a word like cat. It attends it because information about A is recorded in B, and now when it sees A, it can infer that B might fall. And this comes handy because in context learning, because these do not need to be exactly the same. So if something similar to A is recorded in B, and it can output something similar to B. So here we can have A star and B star. When we are A, we can still predict B. So it doesn't need to be exactly the same. So let me just write this. Okay, so this A star, B star, AB. So what I've just written is to say that something similar to A and B can be preceded before, and that still helps us when we see something similar to A to predict something similar to B. And you can see how this comes then handy in context learning. In context learning, we have instances, inputs, outputs of the same task, and then we give a new input, which is similar to other inputs. So we know the output should be similar to other inputs, outputs that we have given as demonstrations. Okay, so hopefully that's clear. As I said, it is really a little bit convoluted. Yes?
So is it useful to look at the QK circuit of the second layer attention? Because in the first layer, all the possible inputs to the attention layer is just the vocabulary. But in the second layer, it's the encoding of the tokens plus the attention.
So I will be honest and say that like following these matrices as we converse about them, it's really hard, right? Like what is multiplied by what? I think the answer to your question is yes, we do need the OE circuits from the second head, because these QK circuits that come from the first and the second head tells us about what is being attended to and what is written. But only the OE circuit of the final or the second layer can tell us what is exactly being used from what is attended. So just to give you an example, I've written this in the notes. For example, we can attend to word bank, the common example of a word with two senses, to disambiguate it, to just make sense of what is the sense of this word in this sentence. Once we have attended to it, we do not need to use it. We can be like, oh, this is the sense of this word. I don't actually need this information to make a next door prediction. So you always need QK and OV circuits, and you do need the OV circuits from the second head because it is the one that makes sense of everything that's being attended to and decides what finally is recorded in the residual stream, and based on that we make the logits. So is this answering your question? I'm not sure that I understood your question right and I'm answering it properly.
So, yeah, my question is, the input to the first head will be bank, right?
Token embedding of the bank.
Yeah, token embedding of bank. But the second head will have bank, but it's looked around and said, oh, it's financial bank. So that's not, with the number of possibilities has increased from size of vocabulary, right?
Number of possibilities for what?
I mean, the size of the matrix is vocabulary by vocabulary. But
this one here, right, is the size of the square in the vocab.
so in the first layer, the number of indices relates to the number of tokens. But in the second layer, there's bank, financial, and bank river as well, right?
Okay, it's a little bit hard to, I would say no. You still are working with square matrices that are square in the vocab. It's just how, like you have all these possibilities of the pairs of query and keys. This is what these matrices that are square in the vocab are, recording. And as you move to a two-layer attention, it's not that now the shapes of these matrices are forthcoming different, rather how you combine the information from them is different. I think it's going to be just progressively confusing if we don't work with the exact equation. I don't know whether this is going to be useful. All right, I'll just show you how these equations look like quickly. But let's take your question offline just to not confuse everyone. So this is an example of how two-layer attention-only transformer, when we derived, everything looks like. And this is where these, I'm taking information from the previous head terms coming into play. So now, I don't think the shapes change at all, but you do have more factors, and how you read them is slightly different. So maybe after the lecture we can look into these, but I would rather not go into these complicated terms because I think we can use the time for more high-level understandings. Okay, so now with all of this, we can define an induction head. And in the experiments by Olson et al., they build up on this foundational framework. And they say, okay, from this foundational framework, we have observed this interesting coping and primitive in-context learning behaviors. So they want to explore it a bit more. So it's a more comprehensive study of what was shown in the mathematical framework work. So in this paper, by article still in the entropic transformer circuits, they define these sequences. They take a random sequence of, let's say, length 50, and then they keep repeating it. And they want to see whether, so this is not an in-context learning task, just to be clear. In-context learning means you have a task, such as summarize something, answer something, it's a proper task, and you give demonstrations about how to complete that task, right? Here we just have these sequences, the repeated sequences of random, sequences, and they say, okay, we are going to study the in-context learning in this syntactic setup, and they claim that this is a proper way to then be informed about in-context learning. And we'll come to whether that is true or not in a few slides. Importantly, because these are random sequences, they are not learned from data, right? So you can't know what will follow let's say, D here, unless you have seen the instance of that in the context, right? Okay, so then they train small 1-layer, 2-layer, 3-layer attention-only transformers, and they are looking into whether any of these attention heads exhibits this behavior. Now your question here comes handy, how exactly are they reading those matrices, and we are not going into that level of detail. But if they observe that the attention head is copying information from the previous token into each next token's representation, and then they define the induction head as a head that attends to the token based on the information of the previous token, not on its own token. Okay, so that's the definition of the induction heads. Now, there might be many heads, and only some of them are exhibiting this behavior, and the analysis is focusing on those. And they present about 5 arguments for why they think that these heads are driving in-context learning. So I won't present all of them, I'll just give you 2 to give you a sense of how these experiments look like. So, first thing on the I-axis, what you see is the difference of the loss at the 50th token in this sequence that we subtract from that loss the loss at the 500th token. The idea here is that if the model is using what's in the context, what should happen with the loss? Doesn't work. Okay. Don't read the I-axis. What do you think?
Should the loss decrease?
Decrease, right. And Matthew, can you explain why do you think it should decrease?
Well, in the case of the 0 layer, I'm not really sure why it would decrease in the 0 layer, just because there's not really too much that's really being done with that transformer circuit, but I feel like, with anything greater than that, loss would obviously decrease, because since we have this sort of pseudo-residual stream going on, that's like attending to more information.
Okay, let's not forget about 0, 1, and so on, other transformers. Just intuitively, why we would expect the loss to decrease if the context was used? Emma?
Because it's just trying to copy what we're looking for, so it should be really that.
Yeah.
If it is able to do it in the context.
Right, so we have a structured sequence, it's a repeated sequence, we take random sequence of 50 whatever, and we just, concatenate these random sequences. So if I give you something like this, you will notice a structure and you will say, it's just being repeated, so when I'm at this token, I just need to copy the next token that occurred in the previous occurrence of that token. Right.
It's just learning diagram.
Not necessarily bigram, bigram basically, but it's a little bit more than that, right? Because it is understanding that if I'm at current age token A, I need to check what kind of token had occurred in this particular context, not in general across all of the possible tokens, and copy that one next. So it's more than just bigram statistics. It's bigram statistics plus the information about the context.
I think they call it skip trigram or something in the paper, don't they?
Yeah, so there is a notion of a skip trigram, which is basically anything that we mentioned that in the previous lecture. So source, destination, and output. Right? So when I said previously, when we are at the destination, we can attach to a token because we know what is the previous token that occurred before the source, and then to predict source as the output. Okay, so here the intuition is simple. If this model is using the context, then it will simply be better at predicting what is the next token, and the loss will therefore decrease. That's why we expect the decrease. And what they show here with the 1 layer, 2 layer, and 3 layer attention-only transformer is that at some point there is a drop in the loss. And they say this is a phase change where the model is learning to do this in-context learning behavior, syntactic in-context learning behavior, and where these induction heads are formed. So that's their first argument. And then they do ablation study, where they ablate those studies. So remember, we can replace them with the mean representation or zero representation, whatever we think appropriate. And when we ablate an induction head, and if we deem that the induction head is what is necessary for the in-context learning, what do we expect to happen with the induction score? So induction score here, or in-context learning score, is the difference between these losses. So if my induction head is important for in-context learning, and I deem this to be a good metric of in-context learning, if I ablate that head, what do we expect to happen with the score?
Drop or get worse.
Get worse. Okay, I like that. That's good. That's good. That's good. Okay, it should get worse, which in this means increasing, right? Because dropping means that we are learning. See, right? Like we dropped means that loss decrease and we actually learn things. If it increased, it means things are getting worse. Yeah. Sometimes it's hard to work with the signs. So here, what we see, this purple is referring to the induction heads. And they're showing that if we apply induction heads, exactly in that phase transition is where the performance or the ICF score will get worse or increase. So these are their arguments, and there are plenty more in their article. I won't go over all of them. And this is the reason why this work by Olson et al. Has been very commonly cited as evidence that these induction heads, which are defined as attention heads that do the following, attends to token based on what happened before them, rather than their own content, and then predict those previous tokens as the next token. This work has been evidence that these induction heads are what drives in-context learning for a long period of time until 2025. And then, because I told you last time that we will see a work by Hume and Steinhardt that shows that they are actually not the primary driver of in-context learning, and something called function vectors is pointing to heads that are driving in-context learning, but those heads identified with function vectors are not the same as induction heads. So what we are going to do next, and I'll come to your question, is we are going to go over what the function vectors are, and then we are going to just quickly go over some of the facts from the Hume and Steinhardt paper over here. Have a question?
Counterfactual question. If you went back 2 slides.
This one?
The one with the random subsequences.
This one?
So I assume the following trivial test has been done that if it created truly random non-repeated subsequences that you would not notice the loss function decrease because there's nothing to learn.
There is something to learn, because if you keep seeing repeated sequences, that's exactly the point. You keep seeing, if I give you...
There's no repeated sequences.
They're repeated, so it's, imagine I give you tokens A, B, C, and then I just repeat them. A, B, C, A, B, C, A, B, C, A, B, C, A, B, C. And I show you this lots of times, and then I ask you, okay, there is A, B, what will come next? You will say C, right? You just seen A, B, C so many times, that's the logical
If
next.
it was a truly random sequence, you wouldn't see the loss function.
There is a key detail here. It's a repeated random sequence.
Yes.
So we repeat the ABC multiple times, right? ABC is random, but due to the repetition, there is structure in this whole sequence, right?
What would happen if there were no repeats?
Then that's not something you can use for this experiment, right? Then there is no expectation that it should repeat, right? So if it's just...
The loss function wouldn't move because there's nothing to learn.
Yeah, exactly, yeah. Unless it's a random sequence from the training data, then there is, But yeah, if it's truly random, maybe once in a while it will guess what's going to be next, but there is no expectation it could. And that's the whole point of being repeated within the larger sequence. Yeah.
Could you go to the next slide?
Mhm.
So you can see that the phase change widens up on the 3 layer,
Mhm.
but then it also doesn't necessarily have a better score compared to the 2 layer.
Mhm.
I guess, is there anything important going on there?
Mhm.
Like, I guess with 3 layers, there's more layers to be used,
Yeah.
and so I guess I'm surprised that like the
Mhm.
score would drop at least a little bit more. And then I guess it makes sense that the phase change is wider, just
Mhm.
because there's more,
Yeah.
I guess, information to process. But
Yeah.
uh,
Yeah, that's an interesting question. I don't really remember whether they made a comparison of two, in-depth comparison of 2 and 3 layer and why the 3 layer one is converging a little bit slower, right? Yeah, unfortunately, I don't know. Sorry about that.
yeah, that's okay.
Okay, so, as I said, our next goal is to define function vectors, and then we are going to go into the analysis by Yin and Steinhardt, just a little bit, not too much, and then we are going to wrap it. Maybe we finish a little bit earlier today, we'll see. Okay, so let me explain function vectors. First of all, you need to now scratch everything we just learned about induction heads, because this doesn't build on induction heads. This is a completely different method, right? So don't think just because today in this lecture we are, continuing with function vectors that it's kind of building on it. Rather, this is a standalone method. But it's going to be a method that's going to find heads that are responsible for in-context learning. But keep in mind that unlike induction heads, which tells us mechanistic process, not only these are the heads, but also what do these heads actually do, how they move information. We won't get that level of detail with function vectors. We are just going to get identification of heads that are responsible for in-context learning. So this is actually a very nice examples of in-context learning. So here you have demonstrations: arrive, depart, small, big, common, rare. This is the task of giving an antonym of a given word. And here we have the translation from English word to a Spanish word. The high-level overview of function vectors is that we are going to take some head, attention head, and we are going to, for each one of these tokens in the prompt, we are going to get the representation of the last token in the prompt that attention head makes. And we are going to do something, average these kinds of representations. And then when we have so-called zero-shot prompt, where we don't have demonstrations, we just tell the model the word fast means, and plug in or patch, now we know terminology patching, is a vector that we have derived from this prompt with the demonstration. It's going to predict what is the antonym of this word. So it's going to say slow, and here the word fast is going to give us a Spanish translation of the word fast, rápido. So now our goal is going to be, how do we define and construct these vectors where we can plug them into a zero-shot prompt and get the representation, the successful completion of the task. Okay, let's see. All right, so for now we are going to then use the whiteboard. This is going to be a little bit annoying today. Oh, it's so much quieter without it's a bit eerie. Okay, let me see. bunch of things. This work I'm going to present it the way it was defined in Todd et al. 2024. But the concurrent work also had presented similar method. Okay, first, so I'm going to define a bunch of notation, and then a bunch of notations will lead us to a certain score, which we can say, okay, this is a score for this attention head being something something, and then this can be used to filter these heads. Okay, so first we are going to use T to denote in T in a set of all possible in-context learning tasks. So this is an ICL task, right? So predict an antony. PT is going to be a set of all the prompts for in-context learning for that task. So a data set. And every one of these prompts, let me make sure, it's a little bit hard to differentiate between my P, which is capital and lower, so I will use this little, like, whatever you call it, to make sure if this one is a lower one. So, we are P. Okay, so a prompt has a few demonstrations, and each demonstration has input and output. So this is the first demonstration. So input, if we have antonyms, if xi1 can be fast and this can be slow. Okay, good. And then finally we have input for which we want the output, and we don't, we don't give it to the model because we want it predicate. So yiq, that's going to be output, the correct output for xyq. Okay, is this clear? So it's a little bit. It's a very mathy way to say something simple, which is every prompt consists of capital N demonstrations of the task, right? So if the task is antony prediction, each one of xi's, j's here is going to be a word such as slow, happy, whatever, and iij is going to be the corresponding antony. So for slow it's going to be fast, for happy it can be unhappy. And then finally, we have a word for which we want the antony, but we don't give it in the prompt. That's what the model needs to predict. Okay, so now we are going to define the mean output of a given head A on these prompts. So we are going to take the size of PT, how many prompts we have. We pass each prompt, PIP. And we record the output for that prompt, for a given attention head. So A is an attention head, and when we have A something, that's the output of, right here, an X. Output of attention head A. At the last token in X. So what is the output of an attention head? Is it a scalar, a vector, a matrix? Vector, right? So if I take the last token in some prompt and I check what the attention head's output for that token is just a new representation of that token that I add to the residual stream. So basically this gives me the average representation of the last token in every single one of these prompts where the representation is computed by a specific attention head I'm looking into right now. If I want to be really precise, I could add something like layer and maybe J denoting in an attention head in a given layer, and out of multiple heads we have in a given attention layer, I'm looking at the Jth one. For simplicity, I won't write that, right? But remember, we have the number of heads equals to the number of layers times number of heads in each layer. Okay, so now we are going to define a shuffled prompt, PI tilde, and the data set is, with all of these will be named capital tilde PI. Okay, so this prompt here is going to have the structure like this one. But except, instead of giving the right output here, we are just going to give a random output. So we are basically going to shuffle these I's here. So the incorrect answer here is associated with each input. Let me maybe write it down. PI shuffled P is going to be, it can be, for example, if I have X, Y, 1, but I have I, Y, I, 3, for example, right? So there is a mismatch. Shuffle in that sense. Everything, you know, and we do that for every one of the demonstrations. So it's an ICL prompt with shuffle layers. The fact that I created some corrupted inputs maybe reminds of something that we learned before. Activation patching. Did you want to say the same?
Noising and denoising and activation.
Noising and denoising. Yeah, so this would be, which version, noising or denoising?
Noising.
I didn't write this, so I don't know why I asked you this. You couldn't possibly answer this question because I just defined the clean and corrupt, but it's still possible we do denoising and noising. But we are going to do denoising. Sorry about that. Okay, so we are going to define a score. I'm going to give two symbols for it because in the original function vector work they call it CIE, which refers to causal indirect effect. In the work by Karin and Jacob Stanhart, they are using a score function vector of A given the corrupted prompt. So let's use both notation because we are talking about both works, so we might see both of them. And it's going to be defined as, okay, since we have just figured out we are going to do the denoising version of patching, anyone feels brave to say what the equation will be here? Can you try to say it first in just a high level? It's going to be in one sentence.
So for the denoising version, would we want to like compute the score with the clean sort of prompts here, and then you do the difference of that with when it's got the corrupt prompts in it, and then I think with that difference, you would take something completely different and see if, I don't know,
You're on a good track, but let's keep it a little bit simpler. So you have said a good thing. We are going to take the, we have a corrupt run, and we are patching with the clean run, right? And we are, you said the score, but let's be more precise. What was the score? What was the function we cared about when we did the patching? Come on, just the logics. The logic, that's great. And if I want to be a little bit more detailed and I want specific logic, do you remember which one I would take here?
Oh, with the ones that want working.
Yeah, exactly. So we know here the correct answer, right? And you knew it. We will take the logic of the correct answer, and we have it with the corrupt run when we patch the corrupt representation of that head with the clean one. And in a normal patching, we would take the logic of the corrupt run and see whether the difference, whether we recovered the logic right out of it. For some reason in my notes I don't have exactly that, so let me just double check what we have here to make sure I do the right equation. Yeah, it's a mistake in my notes, great. Okay, so we basically did the same thing. If this attention head is responsible for, predicting the correct answer here, we would expect to recover lots of the logics for the correct answer by patching the corrupt representation with clean ones, right? So this is why I said, can you just say it in a simpler words, and then we will write the equation. So our function f is going to be probabilities over VOCA. In this work is probabilities. Remember, we actually like to work with logics often more, but in this paper they specifically said probabilities, which means what in every model we have, what do we use to get probabilities?
softness.
You need to say that. I became very good at reading what you are suggesting. Softmax. Yeah. Softmax. And so here we are going to have the corrupt prompt, but we are going to swap the attention, our head, a specific head we are looking into, is going to become this mean representation here, okay? And, okay, so just one thing here, this is the entire softmax, so we are taking the, we are indexing by vocab index of YIQ, which is correct answer. And we are subtracting what is the value for vocab index. Okay, let me just write out. So here I just have my corrupt run, but here I have my corrupt run where the output of the attention head is patched with a clean average representation that we have over here. And we want this, so we want this one to be higher than this one, right? And the more higher it is, the better the patching is, and more indicative that head is of what the correct answer is here, and the task itself. Okay, now a bit more. We then define the average indirect effect just to be the score average across many tasks. So we have a certain number of tasks, and for each task we have a certain number of these corrupt prompts, right? Okay, this is a bit confusing, but. So all I said here, I have calculated this for a single, so for a single one of these prompts. Here I'm averaging across many prompts, many tasks, and still this is just for a single head A. Okay, now this is where things become annoying because I can't show you the results while writing things. But imagine here for a moment that we have some illustration where for a bunch of attention heads we have this score calculated. Then we can see which one of these attention heads have the score to be really high, and we can say these are the top 2%, let's say, of these are the ones we deem responsible for e-context learning. And that's exactly what they do next. So they rank all attention heads by IAI, and then they construct the data set of top 2% of these heads with respect to this. Okay? And those are the ones they call, all right, we think these are responsible for in-context learning. And from those, they help construct the function vector. The basically title of the paper. So I would like it here. We have the function vector for a given task T is the average of these mean representations for the task. Okay, I'll write here now ij, where ij are these attention heads in this top 2% that we have just made. So just to repeat, we have constructed this metric which tells us how much of the in-context learning performance attention heads can recover when we do the denoising patching. And then we took the average over tasks and prompts. Using that score, we could rank all of the attention heads across all layers and all number of heads in each layer. And we can take the top 2% of them by that score. And then we take these mean representation, mean output of each one of these top 2% ones. We average those, and we call that function vector. And that's the vector we're going to use next. Yeah.
Isn't there like some missing fractional term, like the size of A for it to be averaging? Because right now, isn't that just a sum of those means?
Mm-hmm.
So that's not the average of.
Oh, okay, yeah, just a sum.
Okay.
Yeah. Okay, so now, in ideal world, you will have all of what we have written together with the rest of the presentation, but we have to kind of use what we have right now. So try to remember what our vector was while I power everything back on. If you want, you can take a 2-minute break because this is probably going to take 2 minutes to set back up. Oh no, you can still take your break. All right, 2 minutes. Not the simple 1, 2, 3 attention only transformers anymore. So we have 25 and more layers. We have 15 heads in every layer. And here you can see this average indirect effect score. Okay, so this is how they identify just a few of these heads as the one they then use for the function vector. Now I will show you about a kind of few things that they have done with this function vector. So first they have these tasks. They are all pretty simple. So given an input word, generate a word with opposite meaning, capitalize a word, given a country name, generally the capital cities, and very simple stuff like that. Okay, let me go here, I think. All right, so first thing that you can kind of see is in which layers these attention heads live, and very often they live in these mid layers. Okay, this is an interesting result. So here they have different ways of prompting in a zero-shot way. So the word X means and so on. And here from this prompt, whatever you swap the word X with, you want it to completion to be the expected completion of the task if you knew what the task is. And to successfully complete these prompts with a function vector, what they do is, it's somewhat illustrated with a thing here. So here, this is their preliminary result that motivated them to define the function vector we have defined. In this preliminary experiment, they do something simpler, and they just take the average representations instead of the function vector. So imagine here, instead of this symbol, we just had a symbol that we used for the function vector, which was VT, right? So basically, you have your prompt, which has the demonstrations, stop, bottom, go, short, accept, and so on. And you have constructed the function vector from these prompts using all the stuff we had on the whiteboard. And then in a zero-shot prompt, such as simple column, at the column, if that's a separate token, you will swap the representation of a certain attention head with the function vector. And then you might get a completion of the task that is successful. And here what they see is here. If you do zero-shot experiments with these models, they are not so great. But if you add these function vectors, the results are getting much better. Basically, this function vector can recover the performance, and that performance doesn't depend on how we express the zero-shot. It's not that there is something special in the way we prompted to do the zero-shot task. Regardless of how we do it, they can, by adding the function vector, by doing that intervention, they can improve the performance of antonym prediction, which is at most 2.4% here to something that is much, much higher, right? It's not perfect, but going from 0 to 61 obviously is much significantly much better, right? So this is the kind of the evidence that these function vectors are vectors that can recover the in-context learning capability in a particular task. And they do much more in their results. So yeah, you can see if you use function vector, what would be the completion. They have interesting kind of, you can now, you have multiple tasks, you can maybe combine their function vectors and do similar, kind of arithmetic we have seen with analogy problems and see whether you can now do some other task from it and so on. So I will go over the rest of these experiments. For us, this one that it can recover, not recover, recover suggests that there was something good happening in the first place, rather make the model do in-context learning from zero-shot prompt when it couldn't solve the zero-shot prompt. Now we have seen that huge improvement, as if we were doing the in-context learning, but we are having a zero-shot prompt. We've seen that huge boost, and that's a huge evidence that these heads identified through these methodology we have seen on the whiteboard are the heads that are responsible for in-context learning. So now we have induction heads and we have function vectors, and there are both ways to find heads that are seemingly responsible for in-context learning. So the natural question is, are they pointing to the same heads? Is there a huge overlap? And this brings us to this work that I already mentioned by Kyle Yin and Jacob Starkheim. They do a very thorough analysis and comparison of induction heads and function vectors. Unfortunately, I need to close this again, but it's not so annoying as I thought it would be. Okay, to understand the comparison, we need to understand the metric they use. One of them is that in-context learning score that we have seen by anthropic work, but they also have in-context learning accuracy and induction score. Okay, so first of all, they refer to the score that the anthropic work has used as a token loss difference. So this is going to be just the loss of, I will write it like this, at token 50 minus loss at token 500. And that's the one we talked about before. They also, you're going to use what they call induction score. So if we had that a sequence of repeated random sequence, something like this, I'm going to write here with prime, but these are the same. And this notation is just going to help us in a second. Okay. Then we have score induction for a given head and a given random sequence is going to be an average of the attention score, so the one we have in the actual attention metrics, between Ri prime to Ri plus 1. Okay, so how much if we are at the position 49, somewhere later, how much it depends to this position here, which comes next in a previous occurrence of that sequence. And they are going to average it over 1,000 of such random sequences for each one of the heads. Okay, let's get back to their results. So, I said what... Okay, and in-context learning accuracy is just if I have in-context learning prompt, how well I solve the task, right? It's just the accuracy of the prediction. So the question was whether these two mechanisms for finding heads gives us the same heads, and the answer is not really. So the heads that the induction heads work points to, and heads that these function vector scores points to, do not have a major overlap. So these two methodologies are pointing to different heads, and then the natural question is, well, if they are both pointing to different heads, and they are both claiming that they are driving the in-context, these heads they are identifying are driving the in-context learning mechanism, who is right? And this comparison in this work points to function vectors being as the methodology that points to the actual heads, right? So although the Olson work is the one that has for at least 3 years before this work has been published, has been a main reference for what drives, which heads drives the in-context learning behavior, this work is pointing to the different direction, right? And now the heads that the function vectors are identifying are those that you should kind of look in more details if you want to understand what is going on with in-context learning. So let's just go over these results. Let me zoom. I actually have them here, which one is better? Okay, so here. Yellow, these flat lines are just a clean run. With random, we are doing something randomly predicting. Induction is pointing to heads, attention heads that are identified through, checking these two things, whether these heads have this behavior. And function vectors are the attention heads identified through the function vector score. And here we have dashed results where we look at the heads that are function vector heads identified with the function vector scores that do not overlap with induction heads at all. Okay. On the y-axis, we have the ICL accuracy, and here we have this token loss difference. So this is the loss by anthropic work. So first thing here, let's compare the function vector line with the induction headline. What do we see? Which one is lower? Which one? I should say here, importantly, that we are ablating the heads, right? So if we ablate the head and we claim this head is responsible for in-context learning, we would expect the performance to decrease, right? So when we look into these two lines, we see that the heads identified through the function vectors, the loss is lower, right? The loss has dropped more. And one can ask, well, I mean, what about the overlap? Like we are ablating more and more heads, what is the overlap now? The overlap between heads identified through function vectors and induction heads might be increasingly larger. We see that the drop is still very notable even when we look into heads that are identified solely through function vector scores and would not be identified through induction heads at all. And it almost seems like the performance is this gap widens as the model size is larger, right? So in the larger models, it seems increasingly more that the heads that are responsible for in-context learning are those that can be identified through function vectors and not through induction heads. Which is important because the point here is scale matters, right? Maybe if we had 160 million is still way larger than two-layer attention-only transformer, right? That we have looked into Osos's work. So scale matters, and when we increase the size of the model, we increasingly get a stronger evidence that function vectors can identify heads responsible for in-context learning, not induction. I'll come to your question in a second. Now, another important point, we have learned scale matters. Another important point is what happens when we compare these results across two metrics, across in-context learning accuracy and the token loss difference that is used by the prior work. So here we see that induction has actually a bigger drop. And looking at these results, what would you conclude? That induction heads are the heads that are responsible for in-context learning. But the fact is, in-context learning accuracy is the metric, right? Because it is the exact metric measuring in-context learning, right? So there is no question that in-context learning accuracy is a better metric than token loss difference for measuring the effect of ablating a head on the in-context learning capability. So the choice of metrics had mattered a lot, and when we use appropriate metric, we get completely different picture. Okay. Matthew had a question.
Yeah, I'm a bit confused on the visualizations here. It shows that ICL accuracy is decreasing, and we're supposed to say it's a good thing that the function vectors have decreasing accuracy compared
Yeah.
to induction?
So one important thing here is we are ablating ahead.
Oh, okay, so the
Right.
more ablation that we're doing, the more we're messing things up, we should expect the accuracy. to
Exactly,
increase.
right.
Okay.
So just to repeat this point, and it's not here, so I want to make sure this is clear. If I say attention head is an important, a specific attention head in, let's say, layer 2 and a third head, is the head that drives in-context learning or is important for in-context learning. If I do not have that head, what should happen if it's important? My model should not be able to do in-context learning anymore. So that's why we expect the loss from, right? Ablation of important things, if it truly is important, should mess things up, right? And that's exactly why these curves are dropping, right? Yeah. And here the random is to kind of say, if you have a line that's as close, even random can sometimes mess things up, right? So, because everything is connected in transformers, so it's always good to have random baselines. So, if you have, I don't know, you claim a method that drops a little bit, and you say, oh, these 20 heads are important because things have dropped, it's good to have random baseline to see whether, if it dropped as much as randomly picking attention heads to drop, then it's not the interesting result. Okay, so now I want to finish on a more positive note because I do not want you to conclude that the induction head work is useless, right? It's just not maybe, and you should definitely read this paper, and it kind of suggests different things and kind of how to reconcile the comparison. The fact is that the function vectors are pointing to heads that are responsible for in-context learning. By no means is induction a useless thing. So to try to convince you, here is a paper from a very respectful group of authors. It's published a couple of days ago. So again, I haven't read it. I'm pointing to the date just to say that it's still used for the cutting edge interpretability work by the leading interpretability researchers like UUtah and it's just maybe not a mean to explain in-context learning, right? So just the fact that it doesn't point to head that explain in-context learning doesn't make the whole methodology and insights useless, right? It is useful to know that there are heads that do this moving of the information. And in particular, I think this is a really, again, I didn't read this work to kind of tell you it's a great paper, but it's really exciting to see these kinds of methods being used for very interesting and useful applications. So here we have applications in protein language models, and you know that protein folding is one of the biggest recent successes of machine learning. So here they use this whole induction head business to kind of understand how when we have sequences of these proteins, you can find heads that point to end positions back or that are pointing to something repeated and so on. And this kind of stuff is very useful for this data because there is a lot of repetition and structure in that sense. So kind of to wrap, we have seen two methods, both claiming that they are pointing to heads that are explaining in-context learning. Now with this comparison from the last year, we know that function vectors are is a method that points to attention heads that is responsible for in-context learning, but we still don't know mechanism, right? We just know that there is attention head there, but what this attention head exactly do is not what function vectors can explain. And the conclusion we have is not that induction heads are useless now for everything. They have been extensively studied for in-context learning, but we see now the very recent works where they are used for very, very useful stuff, such as understanding protein language models. Okay, let's stop here. Don't forget your deadline next Monday, please. And yeah, see you next Tuesday.